So we want to take a look at the intermolecular forces worksheet. So let me screen share that with you right now. And you got up through problem 19. Okay, so kind of coming back to the end of the section we talked about on Tuesday, let's look at problem 11 and 12. So here we have some hydrocarbons, and they're called alkanes. So alkanes are those saturated hydrocarbons, the ones that don't have any double bonds. And so you've got a bunch of them and their boiling points. And then we've got some different structural isomers of hydrocarbons in number 12. All right, so I'm going to start you off in breakout rooms for 2 minutes just to discuss problems 11 and 12, and then we'll go over them together. Okay, so discuss problems 11 and 12, and we'll go over them shortly. Okay, so breakout rooms. Where did that go? Hey, Chris. Are you online?
Yeah.
Okay. Did you get assigned to a breakout room or no?
No, it just says I have to wait to be assigned.
All right. Well, since it's almost done, what did you think about 11 and 12?
Hang on, I'm gonna get the. Well, I think it seems like the more carbon that you have in there, maybe you have stronger bonds, and thus the boiling point goes up. Maybe.
Okay. All right. So everybody have a chance to touch base about these problems here. So Chris, can you pick a random number 1 through 9?
How about 7?
7. Bold choice. Okay. Michael, talk to us about number 11. What's going on here?
Okay, so well, we can see that. Sorry, my dog is being moved. So when the molecule gets larger, so does the boiling point, and it's fairly regular. And I guess it would be because of I'm completely guessing this, but the London dispersion forces, they're stronger when the molecule is larger, so it attracts, and it would be harder to break it apart into a gas, maybe.
Okay, so absolutely correct in that the bonds that are breaking when these substances go from the liquid phase to the gas phase, right, are intermolecular forces. And I like that Michael specifically identified London dispersion forces as the important force there, right? But I think we can do a little more in detail about like the underlying explanation for why that boiling point is increasing, because I think we can be more specific than just the molecule is larger, right? Does anybody want to volunteer to tack onto that? Yeah, sure, Thomas.
I believe that you have already said that the more number of electrons, the higher number of electrons, the stronger the London dispersion forces are.
Mm-hmm. So absolutely, we want to identify like the main feature of these molecules that's determining the strength of those London dispersion forces.
And then
Okay, so number of electrons is critical, yeah. And then what else do we want to say?
isn't it like more electrons equals more shells?
So these don't
Okay.
have more shells necessarily. Tom, what were you going to say?
Well, I'd assume like configuration of the molecule has some effect. I did like a bit of research, and on one video I looked at it said that like the bigger the surface area, the like higher the London dispersion force. I don't know if that's correct.
Yeah, that's actually really what's going on in number 12. In number 11, the primary thing is the number of electrons. Okay, so we want to say as the number of electrons is going up, right? What does that directly affect about the molecule that's important for London dispersion forces? What's like the critical property of a molecule that allows it to do these London dispersion forces? Yeah, Sophia?
It can be more polar.
Yeah, and what's the exact term that we want to use in an answer like this?
Negative?
Not negative. It has to do with that word polar. It's the same root.
Polarity? I don't know.
Close. Anyone?
Polarization.
Polarizability.
Polarization.
Polarizability.
Polarizability. Oh yeah, that is a keyword.
Okay, did we all write that down in our notes Tuesday? Okay, so here's the thing. You want to put maybe like 7 more big giant stars next to it, because any explanation of London dispersion forces that does not involve the word polarizability is incomplete. Okay? Cannot emphasize that enough. All right? So, what is polarizability? What is polarizability? Connor, can you remind us what polarizability is?
It's I don't remember.
So what do you remember about it? Like, even if you don't have a fully complete definition, like what's going on there with polarizability?
It's like looking at how the electrons get like moved around.
Okay. Yeah. And so we're looking at how the electrons are moving around in these molecules in some way. So someone want to add on to that and give us a more specific, yeah, Tom?
Just how much of an ability does a molecule have to like polarize? So like have electrons on one side and protons on the other.
Exactly. So if a molecule becomes exposed to an electric field, right, where there's a positive and a negative, it says, like, in response to that electric field, like, how polar does the molecule become, right? So there are some molecules which, when they're in an electric field, they don't become very polar, right? They have a low polarizability. Whereas other molecules have a very high polarizability. And when they're in that electric field, they'll become extremely polar and have a very large dipole moment. Okay, and what are the two factors what have we talked about so far that affects the polarizability? Vivian, what's the primary factor that determines polarizability?
The difference in electronegativity.
So difference in electronegativity determines if something's going to have a permanent dipole moment. Okay, so there's a difference between like a molecule being permanently polar or something that can become temporarily polarized. That's a really good point to make. Okay, so there's a distinction between something that is not polar and can become polarized and something that is permanently polar. Okay, so most of the homework was about things that are permanently polar, right? But if we're talking about polarizability, right, these molecules are not polar, right? The carbon and hydrogen don't have a very high difference in electronegativity. The molecules are like relatively symmetric, so they don't have a very large dipole moment permanently. But they can still become polarized, right, if they're exposed to an electric field. So what is the primary factor that determines how polarizable something is? Thomas?
I don't know. We've been talking about how much the electrons can move and also like the number of electrons.
Bingo. Okay. So number of electrons is the single most important factor for determining polarizability. The more electrons that can be pushed around, the more polar the molecule can become. Okay. And so for polarizability, right, we've got number of electrons. And the other thing is kind of the spatial extent of the molecule. And this kind of gets into what Tom was talking about with surface area, right? If you have the same number of electrons, but they're all on the same atom, then that's going to be a less polarizable object than something where you have that same number of electrons distributed over like a very long set of atoms in a long molecule, right? Because there's more ability for them the electrons to move around. Okay. Also, atoms that are less electronegative, right, are going to be more polarizable because they don't hold on to the electrons as strongly. Yeah, Sophia.
So are all molecules that are polarizable, are they also conductive?
They're not conductive, which is also a good distinction to make. That's a great question. So what we're talking about here is not like electrons moving from one atom to another. Okay, we're talking about the atoms or the electrons like on average being like a little bit closer to one side than another. Okay, so if you think about like a molecule like methanol, right? Each of these bonds represents a pair of electrons. You've got the lone pair on oxygen. You've also got a core pair of electrons that are tightly bound to the oxygen and a core pair of electrons that are tightly bound to the carbon. And all of those electrons, they're not static. They're not staying in one place motionless the whole time, right? In fact, we know that they're in atomic orbitals, right? Spatial probability distributions where you're likely to find the electrons. And so it just means that on average, the probability might be shifted slightly more to one side than another, right? And so if all of these like move slightly further north on average, right? And all the electron density can kind of be pulled up a little bit by some kind of positive charge at the top, right? Then that's polarizing the molecule, right? It's not making the electrons move from one atom to another. It's not making the molecule conductive. Electrons are not hopping from this molecule to another one next to it. Okay, so not conductive, but it is causing the electrons to, on average, be a little bit closer to one side than another. All right. Okay. So, right, the number of electrons determines polarizability, and here, as each of the alkanes gets a little bit longer, it's got another carbon atom and another 2 hydrogen atoms. That contributes 8 more electrons each addition. And as we see, the boiling point just keeps on increasing, right? So as the number of electrons increases, the polarizability increases. That causes the London dispersion forces to increase, and therefore the boiling point increases, right? So when you're answering questions like this about explaining how a property changes that's determined by intermolecular forces, you want to start with the underlying structural factor, increased number of electrons, and then explain the mechanism in terms of the kind of underlying model that we've talked about. Increasing the number of electrons increases polarizability, increasing the strength of London dispersion forces, increasing the boiling point. Okay? So just take 15 seconds to make sure you have a clear outline of that answer.
How are you doing today, Mr. Both? Forgot to ask.
It's fantastic. It's Friday. The sky is super blue. Went for a nice little walk this morning. I made banana bread last night, so I'm excited to have a slice of that for recess. I'm doing fantastic. How are you doing, Thomas?
Feeling a little tired. I'm kind of nervous because I have to also start writing my research paper now, and it's gonna be, yeah, it's due next
Started yet, Thomas?
No, I have not.
Your
But I have a
research
plan. It's fine. I did my outline. It's okay. I'm planning. You know. It's fine. It's fine. I'll get it done by Tuesday, and then I'll have 2 days to edit.
Okay.
I'm chilling. But
Everybody else, quick thumbs up, thumbs to the side, thumbs down. How we doing?
I honestly don't know.
Not sure. That's an okay answer too.
I definitely say I'm better than I was a week ago.
Good.
All right. Friday makes me happy. Just, it's hard
It's
to
a good day.
sad on a Friday.
Yeah, it's a good day.
All right, so let's do number 12 here. So I've also sketched the first 2 isomers up here. Let me erase this. And let's see. So which isomer has stronger intermolecular forces? Addie, do you want to take a stab at that one?
We said pentane on the left or the top
Okay.
one.
And why did you say that?
Well, we first looked at the boiling point because it's just a lot higher, or not a lot higher, but a little bit higher. So it must have at least slightly stronger forces. And also the skeletal or the structural, like the way it's set up. I wasn't 100% sure about this, but there's like, it's a lot less compact. So maybe.
Okay, so Addie says correctly that the molecule with the higher boiling point has stronger intermolecular forces. Okay, and then we want to explain why that's the case. All right, and she says that a molecule that is less compact is going to be more, Addie? What's that key word?
Polarizability.
Okay, there we go, right? A molecule that is less compact is going to be more polarizable and therefore have stronger London dispersion forces. Okay, so again, any explanation that involves London dispersion forces or intermolecular forces got to have that term polarizability in it, right? That's how you're explaining this stuff. A molecule with all those electrons spread out over a larger area is going to be easier to polarize than a molecule that's more compact, right? Where the spatial extent of the molecule is small and the electrons can't be moved as far. Okay. Addie, can you pick a number 1 through 8?
3.
3. Okay. Sophia, what do we think about this third isomer here? What do we think is going on with this one?
The boiling point would be in between pentane and neopentane because its surface area is more than neopentane but less than pentane, so it'll like have a medium polarizability.
Okay, that was a triple gold star answer there. Can you say that again for everyone? Because that was perfect.
Its surface area is in between pentane and neopentane. So its polarizability will be in the middle, and so its boiling point will be in the middle too.
Okay, perfect. All right. Any questions about 11 or 12? Okay. So that kind of wraps up London dispersion forces. And London dispersion forces are present in all molecules. Every single molecule is somewhat polarizable because it's got some electrons. Okay, it's just that in some molecules, there are forces other than London dispersion forces, and those can kind of modify how strong the overall IMFs are. Okay, so the other ones that you were looking at for homework were molecules that involved dipole forces. Okay, so let's get some sketches up here. Right, if we think about a fluorine molecule versus the interhalogen compound IF. By the way, what would be the name of that compound? How would we name that systematically? Ooh. Ooh.
Is there a difference? This may not be related, but is there a difference between iodine bonded to fluorine and fluorine bonded to iodine?
No,
Okay, that helps.
they are the same. So how do we name them?
Would we go in? You mean like the standard nomenclature thing? Because I'm thinking like maybe we go in order of like valency. Like they've both got very similar names. So I think whichever one comes afterward would end in IDE, right?
That is correct.
So I hesitate to say iodine fluoride or fluorine iodide because that just sounds a bit too similar. But so would the first one end in IC?
No, it's just the element name. Yeah, Thomas, you want to add on?
Yes. As you can see, there is a single fluorine, so we can say iodine monofluoride.
All right. Iodine monofluoride. Okay, so we remember those prefixes, right? And if the first element, there's only one of the first element, you don't need to put the mono, just like in carbon monoxide. And the other thing is that when you have elements in the same column and you're trying to decide which to do first, the one that's lower in the column is going to go first. Okay. Yeah, useful little review there. All right. So we want to think about what's going on with these molecules. The critical thing is that this covalent bond, right, is made of a pair of electrons, right? There's electron density that's shared between the atoms, and that's what's holding them together. Because of the symmetry of the first molecule, right, this one is completely nonpolar, right? It's got to be nonpolar. It could certainly become polarized temporarily in terms of London dispersion forces, but by symmetry, we can't have a positive and negative side by default, right? How would you choose which one? On the other hand,
Coin? Would you flip a coin?
well, if it becomes temporarily polarized, yeah, it's a 50-50 shot which side becomes polarized. Or it could become polarized top to bottom, too. Like, there's not a super strict, there's no way of determining that ahead of time, right? It's just like random movement of the electrons. Okay, whereas here, with the iodine and the fluorine, they have different electronegativities, right? And a difference in electronegativity, as Vivian pointed out before, determines how a molecule becomes polarized, right? For fluorine, it has a greater electronegativity than iodine. So instead of this electron pair being kind of on average 50% on one side, 50% on the other side of that line, on average, those electrons are going to be a little bit closer to the fluorine than they are to the iodine. Okay? And so that's going to create a partial negative charge over here and a partial positive charge. So a partial charge is indicated by this little symbol, delta. Okay, it's a lowercase Greek d, right, to mean partial charge, meaning not like a full electron has moved completely from one side to the other, but just like a little bit of negative charge on average is closer to one side, right? And so that's one way of representing it with these partial charges. Another way of representing it is by using a dipole arrow. okay, the dipole arrow points from the positive side towards the negative side, okay? So I would put a little plus here and a minus here, and I'm going to draw an arrow through it, right? That's the dipole arrow. Points from positive to negative. Yeah, Thomas?
I didn't figure out how to determine how big we should make the arrows. How do we know that? Is it based on, should we like draw out the, I don't know, the shells or something? I don't know.
It's kind of qualitative, but within reference to the other dipoles in the molecule. So if you have like an example would be a sulfur bonded to a fluorine and a bromine, okay? Both of these are more electronegative than sulfur, okay? And so the bond is going to have a bond dipole that points towards the halogen, right? But we want to communicate that the difference in electronegativity between sulfur and fluorine is greater than the difference in electronegativity between sulfur and bromine. So I might draw a slightly smaller one there and a larger one over here. Okay, so it's really qualitative to just represent differences in magnitude based on differences in electronegativity. All right. So those are the individual bond dipoles, which should be drawn right next to the bond. And then there's the overall molecular dipole moment. Okay, so these add together in a way that it's like you can put the end of one right at the beginning of the other, and where would they end up? Well, if there's like a big giant tug of war, and the bromine's tugging a little bit, but the fluorine's tugging more, then overall, yeah, the arrow on balance is going to point down, but it's also going to point a little bit towards the fluorine, right? So I would draw something like that as the overall molecular dipole moment. And in the simulation, right, the bond dipoles are the ones represented by black arrows, and then the molecular dipole moment is represented by the yellow arrow. So you should have seen the difference there. Okay. All right, so let's do these examples with the geometry, and then yeah. All right, so okay. So for determining overall molecular polarity, the first thing that you do is draw a Lewis structure, and then use the Vissepper theory to draw a 3D picture of it. So after you draw the Lewis structure for water, you recognize two bonds, two electron domains. That's that kind of overall tetrahedral geometry. And because it's got only two bonds, the geometry here would be bent. So we've drawn a bent Lewis structure, right? Whereas carbon dioxide, there's only two electron domains. This is going to be linear, right? And that's going to be critical for determining the polarity of these molecules. All right. Water has bonds that are polarized in the direction of oxygen, right? The oxygen is more electronegative than the hydrogen. It pulls the electron density up and in. That creates an overall molecular dipole moment That's like the addition of those two arrows. Okay. For carbon dioxide, the oxygens are more electronegative than the carbon, and so they also polarize those bonds towards the oxygens. But because this molecule is symmetric, and those bond dipoles are exactly opposite each other, they cancel out. Okay? And so this is a non-polar molecule. Right? There's no like left side being positive, right side being negative. There's no way that you can turn it such that, oh, there's a definite positive side and a definite negative side. Okay? Yeah, Sophia.
Like, couldn't some electrons just like all go to the top? And then
It could become polarized. All right? So it is polarizable, right, based on the number of electrons that are there. But just kind of by default, if it's just sitting there, it doesn't have a net dipole moment like the water does. The water always has a permanent dipole moment. Okay? All right, so yeah, I just want to go over 17 and 18 in the last couple minutes here. Number 15, about what physical evidence suggests water is polar while hexane is nonpolar. There's a video in the drive called Water and Hexane, which I'll have you watch, which I recorded on Wednesday. So we're going to skip that for now because of time, but I want to talk about number 17. Okay, so in number 17, when you've got a data table like this, you want to kind of try and simplify things for yourself and look at, like, all right, let's just compare the molecules that have the same number of electrons here at first. So they're kind of similar in structure, maybe because the top two have more atoms in them, they're going to be slightly more polarizable than the one with the chlorine, because all those electrons are on one atom and chlorine's pretty electronegative, right? We get a measure of how polar the molecule is from the dipole moment. So the the alkane, right, is essentially nonpolar, okay? And it's got this boiling point. Whereas the dimethyl ether and the methyl chloride, they're polar molecules, right? Because those bond dipoles add up, and we have something that's got a permanent positive side and a permanent negative side. And as you can see, that elevates the boiling point by 17 or 18 degrees Kelvin. Okay, so not insignificant. It's not 10%, it's less than 10%, but it's something. Okay, and so I like to think of dipole-dipole forces as a tiebreaker force. Okay. If you're comparing two molecules and they have similar numbers of electrons, but one of them is polar, the polar one will have a slightly higher boiling point. Okay, because they both got London dispersion forces, but if one of them is polar permanently, that's going to make the overall intermolecular forces a little bit stronger. All right. But again, it's a tiebreaker for ones that have similar numbers of electrons. And you can see that being very polar, like the fourth one and the fifth one, can even compensate for having a couple fewer electrons, right? Having 2 fewer or 4 fewer electrons, right? These still have higher boiling points because they're extremely polar. right? You've got carbon and oxygen have a relatively large difference in electronegativity, and there's 4 electrons in that bond. Here, carbon and nitrogen, difference in electronegativity, and lots of electrons being pulled more towards the nitrogen than the carbon, right? These are going to be very polar molecules and therefore have substantially higher boiling points than non-polar or only slightly polar molecules that have similar or even slightly more electrons, okay? But here's the critical piece. If we look at methyl chloride and methyl iodide, okay, methyl chloride was the third one in the chart above, right? So 26 electrons, okay? Quickly determine how many electrons are in methyl iodide. Anyone? How many electrons we got here, Thomas?
Wouldn't it be the same? 26?
No.
Iodine.
Iodine's got a lot more electrons than chlorine.
Oh shoot. Wait. Okay, wait. Oh yeah, chlorine has 35. Okay, 31.
We're not counting just valence electrons here. We're counting total number of electrons in the molecule. How many does each hydrogen have?
1.
1. How many does each carbon have?
8.
No.
6.
6. How many does iodine have?
18. Is it? Shoot, no. 53. Ooh.
53.
I don't know.
For a total of?
53.
What's the total number of electrons?
62. Ay, caramba.
Okay, so here's a tricky point, and I guess we'll go over it at the beginning of next class too. But some people expect that methyl chloride, because it's more polar than methyl iodide, it will have a larger boiling point than methyl iodide. Okay, but they're ignoring London dispersion forces, and that's wrong. Okay, the boiling point of methyl chloride is only around 250 Kelvin. That of methyl iodide is 70 Kelvin larger. Right? It's got substantially stronger intermolecular forces because it's got so many more electrons. Okay? All right, so your homework is outlined for you on the syllabus. So get to it, and I have a great weekend, and I will see you on Monday.
Thanks.